let us start with this computational mechanics by classical as well as finite element approach. Actually, this subject is being taught in this unit 1 and unit 2 according to your syllabus. These are the basic concepts which you should aware before going for the actual problems. So problem solving in this classical approach. First, let us take what is continuum as well as discrete structures. So first, according to all our civil engineering structures, geometrically we can classify them into two types. One is discrete structure, geometrical classification of civil engineering structural systems. Any civil engineering structure, if you take, you can just classify them into two varieties. One is this discrete structure system, next continuum system. This discrete system of civil engineering structures basically made out of by number of members or elements which are having one of the dimension very large when compared to other two dimensions. Because I am telling here geometrical classification. Geometrical classification means it deals with the volume of the structure. Any structure or body, it will have volume. It can be seen by naked eye. That means it has some volume. Volume means it is product of three dimensions. That is length, breadth, as well as thickness, whatever it is, length, width and thickness. So any structure which has volume, which is lying in the space, it has volume, which is having, since it is having volume, it consists of three dimensions. And these three dimensions we always take parallel to three orthogonal coordinate system. Orthogonal means mutually perpendicular coordinate system, mutually. One parallel to horizontal axis, dimension parallel to any horizontal axis, we take it as length. Dimension parallel to another orthogonal axis, we call it as the width. Then another dimension parallel to third axis, we call it as the third dimension. The product of these three dimensions we can just take as the volume of the structure. So if all the structure is made out of by number of members, which are all having one of the dimension very large when compared to other two dimensions, we call such structures as discrete structure system. That is, discrete system means structure made out of by line elements or one-dimensional members. Line means it is having one dimension very large when compared to other two dimensions, because any structure will have elements or members and which has some volume. Since volume is product of three dimensions, and one of the dimensions will be very large in that, other two are small. And if the members are all in a structure, they are all having one dimension very large when compared to other two dimensions, we call such structural system as the discrete system. Example is your columns, beams, a frame consisting of column and beam together. So it is called or an arch. It is curved in shape, that's again dimension. In this frame, if you take beam and column, all the members, beam as well as column, both these members. One of the dimensions, it consists of number of members where one dimension is large when compared to other dimensions. So that means they are all made out of by line elements or linear one-dimensional elements. Such structures which are made out of by line elements or one-dimensional members are called discrete structures, are also called as skeletal structures. They are also called as skeletal structures. And other structures which are other than line. Other than line means it may be made out of area elements or it may be solid elements, three-dimensional solid members, or area elements means two-dimensional area elements. If you take a slab, this slab we can just assume it to be made out of by number of rectangular elements. So this is entire slab. It's a two-dimensional structure wherein two of the dimension is large in this slab structure, that is length and width are large when compared to its thickness. So large means we always take it as a relative term. I am not fixing any number. It is greater than this or less than this. It is just a relative figure. If you see the dimensions, you will see two of the dimensions are relatively large when compared to third one, that is called area element or area member. So if a member in a civil engineering structure is having made out of a number of members which are two-dimensional in nature or which are area. Two-dimensional means area, length and width, which are made out of by area elements. That is called continuum. Area or solid elements. Solid means three-dimensional elements. If you take the pedestal you can assume it to be made out of by number of small brick elements. Right? So that is three-dimensional element. So all other structures made out of area elements which are nothing but two-dimensional members or solid elements, that is three-dimensional members. So all other structures which are made out of by either area elements or solid elements, we call it as continuum structures. So any structure which comes across in space, or it is body. Body means having volume. If the structure, civil engineering body or civil engineering structure, if you observe one of the dimension is large in all its elements, we call it as discrete structure. For example, your beam, or it may be a rigid frame like that, or it may be an arch having supports, either fixed support, inward support like this. All these type of structure, civil engineering structure, they are made out of by only line elements. See, this structure, continuous beam, it is made out of by only straight line element. This is also made out of by only line element. Here, line element. Then all these, we call it as discrete structure, civil engineering structural system, or which is made out of by only line element. These are all called skeletal structure. So otherwise, you have a slab like this, which is supported on all the four sides, either by fixity or it may be a shell type of structure. Right? This sort of structure, which are made out of by only area elements. These are all made out of by number of area elements. You can discretize or you can model structures, right, by area of small figure. That's the area of some elements. Like either it may be rectangles or it may be quadrilaterals or any other triangle like this. We can divide them into number of either triangles, rectangles, squares, number of elements which are interconnected only at finite number of points. That points we call it as the joins or nodes. Here also it is made out of a number of members. Each member which is lying is being interconnected only at finite number of points, which we call it as joint or node. Here also, this, like that, right? So, discrete system is nothing but a system which is made out of by line elements, number of line elements which are interconnected by nodes or joints. Because you will find in this line infinite number of points, infinite number. We don't call all those points within the line as for our purpose of analysis. We don't only finite number of points, preferably the ends of the line. Only the ends of the line. This is one element, another element, another element. The ends of the element are being interconnected to one another. So, and thereby forming the structure, which we call it as a discrete or skeletal structure. Here, it is made out of by areas, either rectangles or triangles, again interconnected only by number of points. That's called nodes. You can discretize a two-dimensional or continuum either by two-dimensional areas or it may be by like that, a brick or three-dimensional brick element, parallelepiped elements or tetrahedron elements like that. Number of tetrahedron elements, a three-dimensional solid body which is called continuum. So it is a continuum system. Here slab, we can assume it to be made out of a number of rectangles. This entire slab covering this, you can take one rectangle, another rectangle, which are interconnected at 4 points, like that, at finite number of points. So that is called continuum structure. By area element or three-dimensional solid elements. That type of elements, a structure made out of an area or solid, three-dimensional members, we call it as a continuum system of civil engineering structure. This is a discrete type of, this is about this first item, that is discrete system, continuous system. Geometrically, any structure which you come across, you can classify them into two varieties, discrete and continuum varieties of structures. And a structure is called discrete type of structure if it is made out of by only line element. So the element may be only one. Then it is called very simple structure, simple beam. It may be made out of a number of lines along a linear direction. That's called continuous beam or continuous line element structure. Or it may be made out of by lines spread out along a line, along horizontal direction as well as vertical direction in a single plane. So that we call it as a rigid plane frame. These are definition of second structure. This is called rigid plane frame structure. This is called simple beam. This is called continuous beam. Continuous beam is having more number of spans. This is only single span. If it has more than one span and all elements lie along a line, then it is called continuous beam. If all the elements lie in one plane, it is called a planar structure. Again, you can classify here discrete system as planar structure as well as space structure. That is planar discrete structure or space discrete structure. So planar structure, discrete structure means if all the elements, line elements in the structure, if they lie in only one plane, either it may be a vertical plane or it may be a horizontal plane. Like beams, columns, either you can treat it as a horizontal plane or you can treat it as a vertical plane. If all elements lie in one plane, it is called planar structure. If the elements lie in different planes, this entire framed structure, you can just suppose if you take like this, number of beams, number of columns like that, interconnected frame structure, beam, column, another beam, column, again interconnected by beams. So this network of all one-dimensional elements not necessarily lying in one plane, in different planes. This lies in this plane and that lies in the other plane, right? So then it is called space structure. So this discrete system, you can again further classify as planar structure or space structure. Here, of course, area, it is always a planar structure. This is a space structure, basically, made out of by three-dimensional solid elements. It is a space structure because all elements lie in different planes. Because it's a brick, it distributes as a continuum in all, it spreads in all the directions. It is called a space structure. This is definitely a space structure. This is a planar structure. Of course, this area element structure made out of only areas, that's also you can treat it as a planar structure because area product of two dimensions. The two dimension forms a plane. You can see two-dimensional lines. It forms the area. Clear? So that is this first topic, that is type of structure, what we have to consider in this particular mechanics. Any structure, they will come under only under this category, either discrete variety or frame structure. Discrete means frame structure. A frame structure is also or a skeletal structure. It is made out of only elements, line elements, which are interconnected by only a finite number of points. There will be number of points. So only a finite number of points only they are being interconnected, and these finite number of points we call joint or node. And between the nodes you have the element or member, right? And all the unknowns what we have to determine during our analysis of structure, we consider only at these nodes or at the joints. All the unknowns which we have to determine during our analysis, we consider them only at the joints or nodes. Similarly, the lobes which these particular structure they are subjected to, they are also considered to act only at the joints or nodes. If a load is acting either on the entire line, length of the line, or the entire area, you are going to consider the equivalent value of the load, equivalent resultant load acting at the joints. Right? So during analysis, this is another important thing which we have to consider. During analysis of structures, all the loads we take to act, we consider to act only at joints or nodes. That is the points where the number of elements are going to be interconnected. The load corresponding to that particular influence where it is there only up to that particular point we consider. Otherwise, best way is to assume each joint or node to be fixed. Whatever load is there between on the member, in between the nodes, we take equivalent joint load. That's what that. Right? All the loads are the internal resistance to oppose that particular load. They are all considered to be acting only at the nodal points. And these loads are considered only at the nodal points, and the internal resistance, because by Newton's law, for every action, there will be equal and opposite reaction. That equal and opposite reaction is called the internal member stress developed. Internal stresses develop from within the member. And that internal stresses in the members due to the load, they are also considered to act only at the joints or nodes opposing the external load. Both internal loads as well as the internal stresses developed, they are all considered at the joints. Likewise, when we consider the forces and loads to act at nodes, and displacements are also considered only at the nodal points. All the unknown displacements which we have to determine during analysis, they are also considered only at the nodes or joints. Right? So that means in the nutshell, all the unknowns what we have to determine during our analysis of the structure, analysis of all these structures, they are considered only at the joints. Internal stresses are this. So if you take a beam member, so loads subjected to loads, so the internal stresses developed in the beams, that is your shear as well as the moment, they have to be considered only at the joints or ends of the member. Internal stresses develop to oppose the external load. The member load we converted into equivalent joint load, and then we have to find out the internal forces developed at the ends to oppose this. So internal forces developed, that is shear as well as moment. So that we will take up next. So these all the member structural system is discretized into number of members or elements, which may be either line or area, or it may be solid elements. If it is composed of only line elements, it is called discrete structure. If it is composed of by area and solid elements, it is called continuum, both. That's called continuum structure. And all these elements are to be considered to interconnect only at the finite number of points, which we define as either joint or node. And all the unknowns what we are determining during our analysis, that is internal forces as well as the displacements, they are considered only at the joints of the structure. And these unknown forces, that is internal forces as well as displacement at various joints, they are going to be determined by three conditions, that is equations of equilibrium, compatibility condition or equilibrium conditions, as well as boundary conditions. Because the end points of the joints, they are called the boundary for that element. Right? The boundary is usually it will have some supports. It may be having some supports, that is called boundary condition. And at the same time, if here at the joint, it is a continuous joint, wherein two members are meeting. Continuous joint means some of the moments at this joint should be 0. That is, m in this horizontal member this vertical member should be 0. That's what we were applying in slope deflection method of analysis. So at each joint, the unknowns to be determined, right? That is displacement as well as forces. They have to satisfy 3 conditions called equilibrium condition, then compatibility condition, and boundary condition. So at each joint or nodes, at each joint, because the entire structure has to be in equilibrium due to the external force, due to the development of internal stresses, structure should be in stable or stationary condition. Stable or stationary means equilibrium condition. So according to equilibrium condition, it says that there should not be any displacement. If there is a displacement in the structural joint, then instability is there. Structure is not stable. Our main idea of analysis is structure should be stable. That means net displacement at all the joints should be 0. So that means when displacement has to be 0, there should not be any force, because the effect of the displacement occurs only if there is a force. If there is a disturbance, then only the displacement occurs. Since displacement should not be there during the analysis, because it has to be in the stationary condition, there should not be any force. That means, what are the types of forces at each joint? Types of force, either it may be a direct force or it may be a moment. Only 2 types of force. So that is, some of the forces should be 0, some of the moment should be 0. So at the end of each member, element, whatever forces or displacement is there. So the end of the members, the forces along horizontal direction should be 0, along vertical direction should be 0, along in the other direction also it should be 0. If it is a planar structure, so the force in the third direction, it is not there. Only force, it may be in the horizontal direction or it may be in the vertical direction. So force, direct force in the z direction, because that any force may be in any direction, but for analysis purpose, we consider always all these forces, we resolve them only acting along horizontal direction, vertical direction, and another normal to that 3 orthogonal direction that we discuss in this coordinate system, degrees of freedom. At the nodes, or since I told all the forces, displacements we consider only at the nodal points, and we have to satisfy the equilibrium condition, compatibility at the nodal points, and boundary conditions wherever the boundary or support is there at the supports. Because some of these nodes may be support. Here it has a 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 support. Here you don't have a support. It's only a joint, right? So only at the support it has to satisfy boundary conditions. That is, at fixed support there should not be any movement, right? So that is, displacement, horizontal displacement is 0. Displacement may be in any direction, but for analysis purpose, we have to resolve them only along 3 axes, right? And the displacement along all the 3 axes should be 0. That is, in other words, forces in all the 3 directions should be 0. The third direction is not considered here because it is planar structure. That is, Fx is 0, Fy is 0, only 2 directions should be 0. Similarly, moment. Moment about x cannot be considered, because moment about x, if you take this as x, moment about x is like this. Correct? This is x, moment about x is like this, it is out of plane. If this is in the vertical plane, so moment about x will be out of plane, it is not considered. Similarly, moment about y it is out of plane, not considered. Only z-axis moment will be only within the plane, so only mz we consider. So in the planar structures, it is only 3. Otherwise, it will be 6. Sigma fx0, fy0, fz0, mx0, my0, mz0. If it is planar structural joint, only 3 should be 0. That is sigma fx0, fy0, mz0. So that we call it as the degrees of freedom. That is freedom for movement. It is there. If it is restraint, it is boundary. Usually at the boundaries, it is restraint. To restrain that, there has to be a reaction. That reaction has to determine. So at boundaries, here, this displacement is not there. Force is not. Force will be there. There must be force to oppose that. So that force is supplied by the support. That we call as the reaction. So we have to determine, during analysis, we have to determine the support reactions, that is boundary conditions, and we have to determine other forces at other joints, all other joints other than boundaries, by satisfying equilibrium and compatibility condition. And equilibrium condition is nothing but sum of all the forces is 0. It is static condition. Equilibrium condition always refers to statics, that's with respect to forces. Sum of all the forces 0. Forces mean there are 2 types of forces. One is direct force and moment. So we have to consider both direct and moment force. So here, direct forces in planar structure along x and y direction, moment about only z direction should be 0. Whereas in general space structure, in that joint, there will be 6 conditions of equilibrium. Forces, direct forces along 3 directions, direct moments along about 3 axes. Direction should be 0. That will be satisfied. This is another basic concept which you have to bear it in mind in our structural analysis. That is about type of continuous system, what are joints, members of the structural system. I have clearly defined types of structures, that is planar structures, space structures, and degrees of freedom. That also I have defined. Degrees of freedom is joints, some restraint is there, that is boundaries, restraint will be there. Other than boundaries, at all other joints, whatever the number of forces or displacement occur, that we call it as the degrees of freedom. So in case of a truss structure, if you take a truss structure, at each joint there cannot be any movement because it's a planar structure. Planar structure, I told you, only 3 displacements, that is translation, 2 translations, horizontal and vertical, and rotation, another z direction. So here only 2 translations are occurring because rotation is not being considered, because each of these truss joints or nodes, they are pin type of joints. Again, these nodes or joints, either it may be pin variety or it may be rigid type. Right? Pin type of node is that particular point wherein the rotation is allowed, but translations are not allowed. Right? There will not be any total translation. Well, rotation is allowed, pin joint. So moment is, rotation is allowed, means no moment, because no restriction, moment developed. The rotation is free to occur. So there is no resistance, there is no moment. So at each truss, which has say support here, there may be a boundary condition, here there may be a boundary condition at these 2 joints. Whereas at all other joints, you have 2 translations. Like that, 2, 4, 6, 8, 10, 12 displacements can occur. So degrees of freedom is 12. Right? But in your syllabus, that's why this particular word is a maximum 3 degrees of freedom. So this particular type of truss, wherein you have more than 3 unknown displacements, because it is a direct stiffness method, only we take unknown as only displacements, not forces. Only if you take displacements, two displacements per joint, other than boundaries. Boundaries here no displacement can occur, here also no displacement, other than at 12, so this problem cannot be solved. Only maximum 3 degrees of freedom is only a truss like this. Only this type of truss, wherein only 2 degrees of freedom is allowed. Suppose if you take this truss, here 2 displacements, here another displacement. It can occur because it is roller. Here each no displacement. Both horizontal and vertical displacement not possible. Horizontal vertical displacement not possible. Here horizontal is possible. Here both are possible. So 3. So it is okay. 3 degrees of freedom. So that is about this maximum degrees of freedom or type of problem. Suppose if you take this beam. In this beam, at each joint, we assume beam to be axially rigid. That means this axial displacement we consider as 0. So only other possibility is vertical displacement and rotation. That's all, because it's a planar structure. Only in space 6 displacement, but in planar structure it is only 3. So here fixed support, no displacement. Here simple supports, vertical displacements are not there. Right? Axial displacement, it is 0 for all the joints. So here rotations can occur. Other rotation both side axis, because beam, each joint is rigid joint. I told you each joint or no, it may be thin or rigid. In truss structure, each joint is pin joint. In beams and frames, it is rigid joint, wherein transfer of moments from one member to another member, it can take place. So here, moment is there, so rotation also will occur. So here 3 degrees of freedom. That is your indeterminacy of the structure, because analysis of structure means it is evaluation of support reactions, that is boundary reactions, as well as internal member end forces and displacements. 3 things to be determined. Internal member forces, member end forces, because only at the ends you are determining those internal member end forces at the joints, support reactions, that is with respect to the forces, reactions at the supports, and end internal member forces developed, that we have to determine. That is only with respect to the forces, that is static unknowns. Portion with respect to forces is static unknown. If you consider displacements, we have to determine displacement also during analysis at each joint. So whatever unknown displacements, unknown displacement is only rotation, rotation, rotation. So that is kinematics. At each joint, we have to determine the effect of unknown forces as well as unknown displacements. What are the forces which we have to determine at each joint? That is called static number of unknown forces, because it is pertained to statics. And number of unknown displacements is called kinematic. So now, all these unknown forces or displacement, it will be determined by equations of equilibrium or compatibility conditions. It has to satisfy If you cannot determine number of forces in the structure at each joint by equations of equilibrium, then that extra forces what you cannot determine by equation of statics, we call it as static indeterminacy, degree of static indeterminacy. Likewise, number of unknown displacements which we have to determine during analysis, we call it as kinematic indeterminacy. After this, understanding the type of structure and where we have to determine these unknowns, what you have to do in analysis. In analysis, we have to determine internal forces developed at the joints, that is at the ends of the members, as well as reactions developed at the support. That is with respect to forces. In addition to this, we have to determine the displacements at all these joints or nodes. Right? So the number of unknown displacement at each joint, it is called kinematic indeterminacy. Number of unknown displacements, which I told here. Number of unknown displacements, it is only rotations, 3. That is kinematic indeterminacy. That is degrees of freedom. Here, 3. This beam problem can be set to equal this thing because you have put a restriction, maximum degrees of freedom, maximum degrees of freedom is 3. Here, degrees of freedom, there is no degrees of freedom, 2 degrees of freedom. That is rotation, rotation. Here, rotation, rotation, vertical translation is not there because if this end moves, this also should move because you assume each member to be axially rigid. Axially rigid means the member should not undergo any contraction or elongation, it should move bodily. That's called rigid body motion. If at all it is moved, it moves as a bodily. There cannot be any contraction or elongation of the member. Bodily it has to move, that's rigid body motion. So if this end moves here or this top, it can happen at this joint. But in this member, this end also should move by same amount because it cannot undergo any axial deformation. So this cannot move. So vertical motion is not there. Similarly here on same argument, if this moves up or down, this also should move for this member, but this cannot move. So vertical displacement is not there. But horizontal displacement if you take, here horizontal displacement is not there, but here it can move. Here also it can move, horizontal displacement. So here it cannot move. So it will be like this. So since this displacement and this displacement they are equal, because bodily it has to move, I told you. This whatever is the length L, this also should be in the L only. So it can bodily move delta, delta. And of course, rotation is there at those 2 points. So these 2 are equal and 2 rotations. So degrees of freedom is 3. And here it is not there. So maximum, this problem is okay, it can be alone. Types of problem I am explaining here itself. Having known what is static indeterminacy, what is kinematic indeterminacy. Static indeterminacy corresponds to number of unknown internal forces at the ends of the members, all the members, which cannot be determined by equation of statics. Because we have to apply equations of equilibrium at each time. And kinematic indeterminacy is number of unknown displacements or degrees of freedom which can occur. So here at each joint in planar structure, in truss it is only 2 displacements, in beams it is 3 displacements strictly speaking, but actually we assume it to be rigid, it is only 2. In rigid plane frame, you can have 3. Horizontal, vertical as well as rotation. But at this joint, vertical is not there, horizontal is there, rotation is there. So 3 degrees of freedom. So that is about degrees of freedom, indeterminacy, and type of the structure, discrete and continuous. I hope I made the points which are there in the syllabus here, because these are all called basic concepts. What is type structure? That means what's a beam? First of all, type of structure. What's a beam? Beam is nothing but a discrete structure. Now I am defining what's a beam. It's a discrete structure where in all members, or wherein it is made out of by line members which are interconnected by rigid joints, and all the L members lie along a line. That is called a beam. If that particular structure, if it has only one span, it is called simple beam. If it has more than one span, it is called continuous beam. And what's a truss? And of course, all member elements lie in one plane. Now, what is a truss type of structure? A truss type of structure is again a structure made out of by laying elements. That means it's a discrete structure. A truss is a framed structure or discrete structure made out of by number of line elements which are interconnected by pin joint, and all members lying in one plane. That's the definition of truss. What's a rigid plane frame? Rigid plane frame is again a planar structure. I am defining using different planar structure. That means it is a structure made out of by line elements. All elements lie in one plane, and all elements being interconnected by rigid joint, not pin joint. What's the difference between this and rigid frame is? Here all joints are pin. Here all joints are rigid. What's the difference between this and this? Here all joints are rigid, all line elements, here also same thing, but difference is all elements lie along a line, then it will be. Here all elements are not lying along a line. This is in different line. This is horizontal line, this is vertical line. Here in beam, all elements has to lie along one direction only. There, all lines can be in different directions. That is rigid plane. So that is about this type of structural systems, and all unknowns, that is displacements and forces. Two types of unknowns. They are considered only as that joints, and they can be either direct force or moments, and generally in space structure it will be 6, whereas in planar structure it reduces to 2, 3 in general. Out of that 3, in rigid plane frames, all 3 can happen at each joint. In beams, we assume beam to be axially rigid, only 2, vertical and rotation. But in truss, each is pin joint, rotation is there, no movement, only 2. So these are that, and accordingly, first you have to observe the structure, you have to ascertain what type of structure it is, whether it is a truss, or that is plane truss, or space truss. If it is space, all 3. That is 3 direct forces. In truss, it is plane truss, it is only 2. In beam, it is again 2 only, shear and moment in this that. So degree of static indeterminacy, you can say it is equal to 2m plus or minus 2j, static indeterminacy. Now I am giving a formula. This formula I am not deriving, it is just by obvious basic concepts. Here m is number of members. Right? In each member in a beam, there will be 2 internal forces at any point. If you take any point, there will be a shear and a moment at any point. So member means we consider start always from the end point, that support. Support, there should not be any displacement. Next, there will be 2. Next, there will be 2. Like that, each member, there will be 2 displacement or 2 degrees of freedom. 2 into m, 2 unknowns at any point, if you take shear and moment. R is number of support reactions. If it is end point, depending upon that, whatever the reaction is there. If it is fixed end, 3 reactions will be there. If it is hinge, 2 reactions will be there. If it is roller, only 1 reaction will be there. So that is number of supports you have to observe, find R. This is number of unknown member and force. This is total support reactions. So this 2m plus R is the total unknown forces in the entire structural system. 2m plus R. At each joint you have 2 equations of equilibrium. Sigma V0, sigma M0. Sigma F, of course, it is actually rigid in beam I am talking about. So that means 2 equilibrium conditions per joint. If you have j number of joints, it will be 2j. So this is the total unknown forces. This is equations of equilibrium available. So unknowns minus equations of equilibrium. This is number of unknowns which you cannot determine by equation of equilibrium, that is static, that we define as static indeterminacy. This is for beams. Correct? Static indeterminacy I am talking about. Similarly, static indeterminacy for truss, it is m plus r minus 2j. That is plane truss. So at each member of a plane truss, right, each member of the plane truss is subjected to only one internal force. That's axial force. Either it may be tensile force or it may be compressive force. In each member, it is only one axial force, like a bar. Bar is also only one. But at each joint, degrees of freedom, movement, it is 2 because horizontal, vertical. Because the inclined member, it will give axial deformation like that. So we always resolve them into 2 orthogonal directions. It will give 2 components. That is degrees of freedom. Is it clear? Don't confuse with static and kinetic. Static means forces only one. Kinematic indeterminacy is 2. Right? But in vertical member, at this end only this vertical is possible. Here also vertical is possible. Horizontal we have to take it as 0. But inclined member, so this displacement is there, that's along the inclined direction. Always we resolve them into orthogonal direction for analysis purpose. It gives 2. Here horizontal member, only horizontal displacement is there, vertical is not 0. It has to be taken as 0, like that. So forces, displacement together have to take. The concept of force, statics and concept of displacement should be very clear. I hope that in undergraduate level it has been studied in detail. Here the only basic concepts and revising all those knowledge. So that is about for truss member. When I will talk about the degree of indeterminacy, in each member you have only one force, that's axial force. If you have m number of members, means m into 1, m. Or of course support reactions. So here it is hinge, 2 reactions, 2 reactions. Totally R is 4 we have to take. And each joint you have 2 equations of equilibrium. Fx0, Fy 0. So if j number of joints means 2 into j. So this is total number of unknown forces to be determined in this entire structure. This is equations of equilibrium. This is number of forces which we cannot determine by this equation of statics. That is degree of static indeterminacy. In truss, in plane frame, it is 3m plus r minus because in rigid plane frame, any point you have three forces: axial, shear, and moment. In beam, it is only shear, moment. Axial is zero. In truss, is only one. So here, per member, 3, which is m number of members means 3 into m. R is of course observed in support, type of support, whatever the reactions which are there. So you have to add 3m plus r. And each joint you have three equations of equilibrium: Fx0, Fy0, Mz0. So this total force, unknown force, minus equations of equilibrium. That is about this static indeterminacy. Is it clear? We have this formula for static indeterminacy. And kinematic indeterminacy is of course unknown displacement. That's very simple. At each joint of the truss, we have two displacements. If j number of joints means 2j and minus r. R is support reactions. At supports, you have some displacements not possible. Because of that only you have reaction force. Right? So it is then 2j minus r. Kinematic indeterminacy. This is for truss. At each joint, 2j number of joints, 2j, R is support reactions. That is the support restraints. At those restraints, there won't be any displacement. Because of that only that reaction force is there. So this 2j, total number of displacement minus displacement which are not possible, that is unknown displacement. That is kinematic indeterminacy. So in case of this is plane truss. In beams, Ki 2j minus r. Again, in beams, two displacement, shear, that is vertical rotation. Here, no displacement is possible. Here, vertical is not there because of support. Reaction is there, no support. Only rotation. Here, only rotation. Here, only rotation. So 1, 2, 3. So that means it is 2j, two number of joints, 1, 2, 3, 4. 2 into 4, 8, minus r is here 2, 3, 4, 5. That if you do it, you will get 3. Right? So 8 minus 5. So 2j, 2 into j is 4 minus r, 2 reactions. Though you have 3 here, axial reaction we neglect, I told you. So 2, 3, 4, 5 minus 5. So 8 minus 5, 3. Kinematic indeterminacy is 3. That 3 is these rotations. Similarly, in rigid plane frames, it is 3j minus r. Rigid frames. This is for beams which are axially rigid. This is truss. This is plane. That is for kinematic indeterminacy. So we have defined this type of structure. We have defined indeterminacy. We have told what is degrees of freedom. Degrees of freedom minus reactions. The other one in the overall structure, because now I told you degrees of freedom is 3. Whatever that, final, after deducting that support reactions from the joint displacement, So whatever we are determining, that static indeterminacy, that is kinematic indeterminacy, that is called degrees of freedom. Is it clear? That is about all these three basic concepts. Next comes these coordinates. Right? There are two types of coordinates which we define. Of course, here the coordinates, whatever I have considered, is our usual Cartesian coordinate system along x, along y, along z. Whatever direction, whatever the direction of force, we can resolve. Whatever direction of displacement, we can resolve into these for analysis purpose. Always. After that, some will be happening, some will not be happening. So, whatever actual which happens, that corresponds to our degrees of freedom. Otherwise, in general static indeterminacy, kinematic indeterminacy, whichever happens, that is degrees of freedom. That we have to ascertain clearly. First, before doing the analysis, we have to observe type of structure, type of unknowns, both forces as well as displacement, corresponding to coordinates. I am talking about now the classical method of analysis. Classical approach of analysis is, first we have to identify the structure, then we have to identify the unknowns, both forces and displacements, degrees of freedom. And third one, so those unknown forces and displacements with respect to the two types of coordinates. So the first one is whatever just now I have defined, the unknown forces and unknown displacement is all with respect to a general coordinate system, that is called global coordinate system. Global coordinate system. It is also called as system coordinates. System coordinate or global coordinate, wherein always one of the axes is chosen along horizontal direction, other two axes are orthogonal to it, that is perpendicular to that. One of the axes you fix either always in the horizontal direction, other two normal to that. One in the plane, another normal to that. That's all. You cannot have any other thing. So all the forces and displacement corresponding to this, we call it as global coordinate system of forces or system coordinates. So any member, if you take a plane member, plane frame member, either a truss member or a beam member or a rigid plane frame member. So at the ends, wherein it is being connected with other elements, right, we consider the unknown. That's what I told. It consists of number of elements connected only at finite number of points called nodes or joints. So here nodes or joints are only ends, that is 2. So here you can have plane structure, 3 coordinates, here also 3 coordinates. That is global coordinate system. So when forces or displacement unknown, you have to mark with respect to this. As I showed you in continuous beam, 3 rotations or translations, you have to mark it at the nodes of each element. This is called with respect to coordinate system or system coordinate axis. Then there is another system of coordinates which is called, wherein one of the axes is chosen is the centroidal longitudinal axis of the member. This I am talking about with respect to discrete structure. If it is a continuum structure, the centroidal horizontal axis we have to take. always centroidal axis. This global axis may be anywhere. With reference to that, we have to identify the coordinates of the nodes with respect to fixed horizontal direction, with respect to fixed vertical direction, with respect to the third direction, we have to establish the coordinates, x, y, z, coordinates of all the nodes. Whereas that is global coordinate system. That is everyone is well versed. With respect to another coordinate system, that is called local coordinate system. Coordinate system. Or it is also called as member coordinate system. Here it is structure coordinate system. Total structure. Here it is local within the member. So the axis of the member, longitudinal axis or centroidal axis, is chosen as one of the coordinate x dash, this is y dash. So one of the axes is chosen as the longitudinal centroidal axis is chosen as one of the axes. Other two normal to it is chosen as other two coordinates. Here always one of the axes is horizontal, other two normal to it. Here it is always along the longitudinal horizontal axis, longitudinal centroidal axis. Longitudinal centroidal, it has to pass through the center of gravity of the member. That we want to be aware of it. Along the longitudinal direction, along the dimension which is large, in other words, that is chosen as the axis, that is local coordinate system. So usually the internal member forces which have been developed at the ends are chosen here, internal member forces like that. They are chosen with respect to global axis, local axis. Internal member forces to be determined is always with respect to member axis, internal member forces. Or internal displacements, member displacement. That's the internal energy stored. That is always with respect to local axis. With respect to global, always external loads acting as well as the any other displacement, temperature change, settlement of support chain, all these are with respect to global coordinate system. So global coordinates, so always represented external loads are expressed with respect to this, with respect to local coordinate, internal end forces. Internal end forces are always developed with respect to local coordinates. Any other external loads, they are with respect to global. So, when external loads we consider in the global direction, because all loads are gravity loads, that's perfectly acting in the gravity direction, all loads usually. Wind loads, it may be in any direction, that we have to take normal always either sideways, in any direction. So that's an earthquake load or wind, your blast load, whatever it is, any type of loads, always we resolve along global direction. Internal forces develop, that is your internal axial force, shear and moment in planar structures. Otherwise in space structures it is 6 internal forces, they will have to be along local directions we have to consider. That is this coordinate system. And degrees of freedom also we have to define. In the general way, it has to be defined with respect to local and this. Then we have to interrelate this. Because during our analysis, loads will be in global direction, internal forces we have to determine in into direction. As long as the members, they are perfectly horizontal or perfectly vertical, orthogonals, truly 90 degrees members, no problem. But the moment inclined members are there, inclined elements, the problem starts. So because when we determine in loads and when we determine intermember forces, they will be in different directions. So we have to interrelate. So there actually the problem comes. Loads, well, there is no problem at all, always fixed with global direction. But when we are determining the internal resistance, stresses, which has to be invariably in the local coordinate system, because it has to be along the member, this thing only we have to define. We cannot just define in any direction. It happens actually in any direction. But for analysis purpose, we select it to happen along the axis, along the local coordinate system, one system. So when we see the one in perfectly horizontal, perfectly vertical members or elements, no problem issue occurs. But the moment there is inclined members, then we have to interrelate them, either forces or displacement. That is called this transformation matrix. Displacement. Here we talk about displacement because we are talking about only stiffness method, wherein we are interested only in the kinematics. That's displacements only, not forces, right? So that transformation, coordinate transformation from local to global or global to local, we can always interrelate them by what is known as transformation matrix. Right? This is that transformation matrix. Is it clear? So there are two types of general coordinate system wherein we define the system of forces, system of displacements. System of forces and displacements you can define either with respect to a global coordinate system, because it can happen in any direction in practice, but we always, for analysis purpose, we resolve them along only one coordinate type of system, that's global system or this coordinate system. But the internal forces developed, we define with respect to another coordinate system, that is internal local coordinate system, and they have to be interrelated by what is known as a transformation matrix or coordinate transformation matrix. So that I will tell you. So how to tell it that? The stiffness I will define, then we can go straight away for problems. I have covered almost everything. Whatever things which are there, I have covered. Now I will optimize these things, all these things now. Now, coming for analysis of structures. Either it may be a truss or a beam or a jet plane frame structure. In analysis of structure, analysis of structures involves determination of internal forces and internal member or element forces developed. Forces are sometimes stresses, internal involves determination of internal member or element forces developed at the ends of members and support reactions. Internal member and forces at the ends of members and support reactions, as well as displacement at all joints. So this is with respect to forces, this is with respect to displacements. So that is statics, this is kinematics, both. It involves both this. And due to external loads or disturbance. Right? Now these external loads generally all external loads and displacements at joints are considered with respect to global coordinates. All external loads are always with respect to loads. And displacement, because we have to measure if there is a settlement of support, it will be there, it has to be again load given. Temperature again, it has to be with respect to load only, it has to be in global direction. So, in general, all displacements as well as external loads to be in the global direction. Right? So, and all internal forces develop, it has to be with respect to global. So, in all internal member and forces to be determined will be global coordinates. So this is a very, very important aspect in this matrix method of analysis, in the classical method. Because hitherto we talk about only the forces corresponding displacement, forces and displacements. So forces, external loads, internal forces develop. The external forces with respect to global, internal with respect to displacements, that again has to be with respect to this. So having known this now having known the displacements and forces, we have to interrelate the forces and displacements in the global direction first. We have to interrelate the external loads and the displacements at various joints. We have to determine the displacement because of the external load, because only at the loads only we consider at the joints nodes, having discretized the structure either in the form of lines or in the form of areas or in the form of this that is having defined joints and members. You have to define the members, you have to define the joints, you have to identify the degrees of freedom. That is a known displacement. What is the degrees of freedom? In trusses, horizontal, vertical. In beams, vertical displacement and rotation. Generally vertical will not be there, it will be only rotations. In rigid plane frame, axial, these are all planar. In space, 6 you have to consider, depending upon joints. So that is having marked, degrees of freedom to be marked, joints to be marked, coordinates to be marked. That's with respect to global coordinates. That first. And also coordinate geometry, length, everything, direction, cosines, everything. That's coordinates with respect to global. Then the internal forces. We have to identify the internal member force or element information. We have to formulate. Carefully you observe. Whatever I am talking about, it has sense now. The essence of analysis. The internal forces are always with respect to element coordinate. Element coordinate means always first in the element we have to identify the origin. Then one axis. One axis has to be linear direction, large axis, that you know, along the central axis. So the origin, we always, each line element if you take, always each element it has two ends. One end we call it as a node I, another end we call it as node J. The direction always, origin we can select I or J. There is no restriction in case of discrete structure I am talking about, or in case of area element also, either this rectangle or it may be a triangle element, whatever it is, area thing. Here also, with respect to this, you have to select this origin, and these are the nodes. With respect to these nodes, we have to identify. Here, we have to identify one origin. Generally, we select one of the nodes, either I or J, as the origin, and axis from I to J. If you select J as the origin, J to I is always taken as positive local coordinate direction. That is, because force and displacement both are vector quantities, we have to give importance for sign, direction. So always choose this by giving the joint information. You have to see for each member which is node I, which is node J. You have to define joint information. And that they call element connectivity, that we have to define in finite element approach. But in classical, we need not have to bother. Simply we can take one of the member axis because it is very much simple. But in computer, the finite element approach, we have to always define local axis origin. And positive direction is always from node I to J. Element we always define as I to J. This is the origin. And of course, other two axes, normal to that, is fixed. Other two coordinates. One we have to select. This is another important thing which we have to bear it in mind. So having understood this, so standard notations. Gives them a force, standard notations, and also force, displacement, relationship. that is this. I have rubbed it out. Force displacement relationship, concept of stiffness. That is concept of stiffness and flexibility. So, see. So within domain of elasticity. You know what is meant by elasticity? Elasticity means, so elastic means if the applied force is removed, the member or body will regain its original shape. When force is there, there must be some deformation is bound to occur. Whenever force is there, work has to be done, and there must be some deformation. That is, work is in the form of deformation, energy change. So whenever there is a deformation, work is done, and when you remove the force, if that deformation, whatever is there, if it becomes zero, or if the member attains its original shape, then it is called elastic. So within that elastic domain, we say force is directly proportional to strain or displacement. After all, strain is nothing but ratio of change in length to the dimension to original dimension. Both it's a ratio, non-dimensional quantity, so we need not have to bother whether it is strain or displacement. Right? So that's why strain means displacement I am talking about, because it's a non-dimensional figure. Force is always proportional to displacement. Fd, if you plot a curve, this force displacement relationship always it will be linear. If you apply a force, right, up to certain force, then if you remove it, it will come back to original shape. That's a linear variation, directly proportional. So force is proportional to displacement. That is, if I use the notation for force as P, displacement as D. That's what I am defining here. Force displacement relationship, standard notation. So we can always say P is proportional to D within the elastic domain. So or we can say P is equal to KD, or this D is proportional to D, converse. So D is equal to some constant into P. I can write now, we are directly proportional, some constant. And this constant, we call it as stiffness or flexibility. Within the elastic limit, force is always proportional to displacement, or you can say P is equal to some constant into displacement, or vice versa. Displacement is equal to some constant into force, where is K is called stiffness and F is called flexibility. This is what the concept of stiffness is. It's a very simple, basic concept. Because we are talking about elasticity. Within elastic limit, force is proportional to displacement. That's straight line variation. Whether it is force displacement curve or stress strain curve, it has to be linear. So it has to be this. So this is called stiffness. Now you can define stiffness. So in this equation, if D is equal to 1, P is equal to K. That means stiffness is defined as, at any point is defined as the force due to unit displacement. Correct? So P is equal to K. That is stiffness K is defined as force developed due to unit displacement. So always we have to apply a unit displacement along that coordinate. Wherever it is occurring, we have to find the corresponding force. It is called stiffness. Likewise, if P is equal to 1, D is equal to P. That means flexibility is defined as the displacement developed due to unit force. Whenever you want to develop flexibility at any point, and that degree of freedom direction you have to apply a unit force, find the displacement due to that unit force in this structure. You will get the flexibility. Is it clear now? I have defined the concept of the flexibility, and this is true if there is a one force and one displacement corresponding to that force, displacement, or whatever it occurs. If you have a system of forces, in practice we have number of forces or number of loads, P1, P2, P3, resulting number of displacements, D1, D2, D3, then the relationship is matrix notation. See, vector P should be stiff matrix K into matrix K. Because matrix after all is nothing but group of elements. When you have number of system of four quantities, you have to group all of them in matrix notation. That's what I'm telling you. Standard notation being used. One force proportional to one displacement. If a system of forces resulting in system of displacement, so we can say if we have a system of forces P equal to P1, P2, P3, etc. Then transpose, because it is always a vector quantity, so transpose only is vector, it's a vector. That's why I am writing T is to save space. I am writing instead of vertical direction, I am using horizontal direction with a transpose. You are well with it. Transpose. Transpose means a row to be changed into column, that's all. And resulting in corresponding displacement D is equal to D1, D2, D3, etc. Dn. Then one can be written as P is equal to P where K is called stiffness matrix. Likewise flexibility, because we talk about now only stiffness method, direct stiffness method. That is the relationship between force and displacement. How to generate K, that also I have told now. K, J, any element, it consists of ith row, kth column. right? So Kij, any element, Ij, Kij, you can determine by applying a unit force J along J is equal to 1. Whatever force developed, a displacement occurs at I, you find out. That is Kij. Like that, each thing it can be related. That is matrix notation. Force displacement relationship is equal to K. So, in general, so the analysis of because next I will go for working problems. So before working out problems, I will generate a general notation. Because since these force and displacements, they are related to two types of coordinate system, I am using this general notation. PS is vector global forces with respect to or vector of forces. Vector of forces with respect to global or system coordinate. Similarly, PM is vector of forces with respect to local or member coordinates. That's the notation. Here I told P. There are two types of P's. One is with respect to global system, another local. This is the notation I will use. PS is always for global forces, member forces, local coordinate forces. Likewise, DM or DS is vector of displacement with respect to global system, and DM is vector of displacement with respect to local system, and PM is equal to KM DM. This equation, force displacement, where PM is vector of element forces, vector of element displacement. This is stiffness matrix with respect to local coordinates or member coordinates, and K is similarly PS is equal to KS DS, and KS is stiffness or global stiffness matrix or system stiffness matrix. This is element stiffness matrix. This is global or system stiffness matrix. And this DM, the local coordinate displacement, is related to global displacement. They are again interrelated, transfer, local to global. And this R is called transformation matrix. all the concepts, I hope now I made it clear. Local, global coordinate system, local forces are what, global forces are what, global system stiffness matrix, local stiffness matrix, because now I am resorting to matrix method of analysis, matrix operation. So we can use MATLAB, we have standard program available, all the operations are only matrix operation. So knowing PS, here PS is equal to KS PS, knowing KS and PS, this we can find element property, major thing. Load, external loads, PS is always external load with respect to global coordinate, you can evaluate DS. DS is nothing but KS inverse PS. KS inverse, you can do that matrix operation, multiply by PS, vector of external loads acting at the nodal points, you can evaluate DS. Then you can interpolate DS to DM, then evaluate DM, having determined transformation matrix, then having DM, you can find out here. Km can be determined with respect to local area. So that is your entire analysis. Whatever may be the number of system of degrees of freedom, system of coordinate, degrees of freedom, of course if it is very few, maximum 3 we can do by hand. That is what was chapter in unit 2. Is there, I have got some problems in unit 2, indicate all these. Then for complicated problem, you can use any standard programming and you can write a program on your own with these basic concepts. It is there, MATLAB code, you can write it, or any other standard program, C language or any other language which you are well versed, you can write program, have an understanding this, you can do a matrix operation and come out with itself, whatever may be the n number of unknowns, n number of steps. That is actually the subject procedure. So, having known this, only this to be determined, we can say here this Rij is the displacement along element coordinate I due to unit displacement along J unit displacement along J system coordinate. That is important definition. To generate this transformation matrix. This is so you have to identify the element coordinates for the forces. You have to identify system coordinates for forces. So force and displacement. For displacement, system coordinate, forces, element coordinate, apply unit displacement, find the corresponding displacement only along the element coordinates, that is component, that is all. Then if you multiply by that global displacement, you will get the corresponding. That is your transformation matrix. This definition or concept you have to remember while working the problem. This you have to be very, very careful. I will explain it with respect to the problem and this, so we can just come out with the analysis result. This is about the entire unit 1 of the syllabus. Now only problems. Trusses, beams, then 3 problems. I have worked in extra that covers unit 2. Then we can say problem you can, after explaining the basic concepts of finite element approach, similar to this classical approach, finite element approach, I will explain same this thing. We have to arrive at the same matrices, matrix operations. So we have to perform. So only generation of this Ks is by different approach, finite element approach, nothing other than that. Either Ks or Km. We have to generate either by finite element approach. Here, classical approach I will do with respect to the, or if you have another 10 minutes, I can develop Km stiffness matrix for a beam element or one truss element. Plane frame also, combining beam and truss, you will get plane frame. Because truss is only axial. Beam is shear and moment. Plane frame, both axial, shear, beam. So if I develop for truss and beam, so for plane frame you add the two with that degree of freedom. So you will get a plane frame. That's all. If under 10 minutes I can take for developing member stiffness matrix of truss, the plane frame element. I will show you, right? It takes just 5 or 10 minutes. So then we can straight away, for one element if I know, I can assemble all the elements, get the total overall Km matrix. Then I can use that transformation matrix to get Ks by what is known as principle of contragradients. So first I will develop the Km matrix. So member consider we are talking about only member stiffness matrix, local coordinate. And I am talking about only bar or truss element, it is a line element. Right? Both are clear now, because I have told you types of structures and everything. So consider a bar or truss element. Consider a bar or truss element Ij in local coordinates. Because always it has two ends. Local coordinate I am talking about, origin is always I will take, J is the next node, this is that local coordinate axis. This is the origin. This is your normal to this is your y dash axis. I am talking about only local. Ij. One end, then or 1, 2, you can call it. How many degrees of freedom it will have? Truss element in local coordinate, it is only one, axial force. It is subjected to only axial force. Only one force. Correct? Huh? So only 1 degree of freedom. So this is di or pi. This is dmi. This is EMI, or this is DMI. J or PMJ. When force along the member coordinate at J, force at the R displacement corresponding, that's the notation I am using. The force or displacement. Positive direction I am taking like this. Origin I will select always I. I to J is the direction of local coordinate. I hope everything I made it clear now. This is the element. Having length AE axial dt. Area of cross section A, E is the modulus of elasticity of the material of that bar element. It has only 1 degrees of freedom. Now, I have to apply equilibrium conditions. I told you, it is for analysis purpose. Correct? Huh? So I will apply. How many equations of equilibrium I have to apply? 2 equations of equilibrium. Sigma x is 0, sigma y. Here it is only in local coordinates, only 1 equation. In other direction, there is no force developed. Right? So sigma x is equal to 0. That means PMI R I will use, okay, PMI is plus PMJ is equal to 0. Sum of all forces in x direction, x dash is 0 in local coordinates, equilibrium condition. We have got the equilibrium condition, two conditions for finding the unknowns. Correct? Then R, I can say PMI equals minus PMJ. So hence, and there will be only one independent, unknown internal force. Internal and element force. Because we have to determine internal element, out of 2, one is equal to other and opposite. So that means out of PMI and PMJ, by equilibrium condition, you will find PMI is equal to minus PMJ, only one independent force. Correct? So that means only one unknown internal force to be determined. That is PMJ. Correct? Net displacement. Of course, displacements will be different. Load also may be acting. Here I didn't consider any external load. If load is there, then these two displacements will be different. So they are independent. DMI is independent, DMJ is independent. But as far as force is concerned, for equilibrium condition, so they are not independent. That's why the flexibility method is ruled out. Only displacement, independent number, only we are taking it is predominant. That is, of course, don't bother about that. Why we highlight only displacement of stiffness method is because of this. Because that's only independent. Forces need not be independent. In stiffness method, flexibility method, force is the unknown. In displacement method or stiffness method, displacement is unknown. Only the unknowns are correctly matched. whereas forces cannot be independent. That is suggested. So no acting forces. Now net displacement in element is equal to dj minus di. Here displacement is of course dmj dm. Net displacement. This goes this much, this. Net displacement will be that minus this in the element. Both are moving, right? The net displacement is whatever this has moved minus this has moved. That's the actual net displacement in the element. This is called delta. Therefore, strain is equal to delta by N. Strain is that. So that is nothing but dmj minus dmi divided by N. Stress sigma is equal to E epsilon. It is within the elastic domain. Stress is proportional to strain, or stress is equal to some constant in the sense that is modulus of elasticity. So that is E dm j correct? Therefore, force equals sigma into area. Strain, these are net displacement. Strain, net displacement in divided by original length. Stress is nothing but E into epsilon, because stress by strain is E, therefore that is E epsilon. So force is equal to stress into A. Stress into A. Stress is force per unit area. So this is nothing but AE by N is dmj minus dmn divided by dmj minus dmn. Force. That is force here. Not with FMJ, it is PMJ. PMJ is the force. So when this is known, PMI, we have found out, so stiffness matters. I can write. So, therefore, PMI is equal to minus PMJ, that is equal to minus LE by L dmj minus dmi, or it is equal to AE by L dmi minus dmj. Correct? This. Therefore, PMJ, PMI, PMJ in matrix notation equals, in matrix notation, right? AE by L one minus one minus one dmi. You see whether it is right. PMI equals AE by L into 1 into DMI minus DMJ. That is your PMI. AE by L DMI minus DMJ. And PMJ is equal to AE by L minus DMI plus DMJ. Matrix multiplication. It is that. So this is nothing but your PM forces at the ends of element, correct? Is equal to, this is nothing but stiffness matrix. This is DM. So this is Km or, right? Where Km is equal to Truss element, stiffness matrix, truss element of length L, any element L, AE accelerated having local coordinates with I as the origin, J as the other node, with these end forces corresponding to displacements. I have obtained the relationship between force and displacement through a stiffness matrix. All what hitherto I told you, stiffness matrix. Or now we can define stiffness matrix in a different way. It is nothing but, stiffness matrix is nothing but the relationship between the member end forces to member end displacements. Independent member end forces we have to use. It is the relationship between independent member end forces and the displacement. That is defined as stiffness matrix. So now I have given the expression member and stiffness. Km is known, right? Like that, Ks can be determined, right? So Ks coordinates are this global, horizontal at I, horizontal. Two will be there. With member local, only one, right? Only one is there now. With global, there will be two. So this is U1, V1, U2, V2, 1, 2 if you call. I as 1, J as 2, right? Then this will be U1, U2, U1, V1, U2, V2. Then you have U1, V1, U2, V2 as the displacement. So you have, for a plate truss element in global coordinates, you can develop this stiffness through transformation matrix. So straight away from member to global, I have, by principle of contractility, that I will explain in the next class. Principle of contractility, then local to global, we can just derive. Now you remember this KL, stiffness matrix for a bar element. Of course, member element, local coordinate only, is given by AE by L, axial rigidity of the member. The pure geometry is only. Area is geometry, area, length, area is geometry only. Material property, AE by L, 1 minus 1 minus 1. You can easily, like that for all the members, you can write it. Assemble, you will get global unassembled stiffness matrix. Then you transform global, then use acceleration. That's all. Analysis is very, very simple. Only you can write a program easily, so it won't take more time. You can write easily the program, do for any number of coordinates. Okay? beam also will write 2. One beam also will develop. Next time we take for global. Beam element. Beam I told is a very still simpler than this truss. Because beam is always told to define all members lay along a line. Global and local coincides. Right? How I define the beam? It's a one-dimensional element when all elements lie only along a line. And local axis along that line. Global axis horizontal only. They are coinciding. You see the beauty. So that's why beams are simpler. So if you take a beam element, so this is your x as well as x dash. But if the beam is inclined, like a rigid frame, either vertical or this, then it is different. Now I take for beam, I am defining. It is only horizontal. So beam, whatever element stiffness matrix, it will be global also. So beam member, I will say 1, 2 instead of ij, I will call it as 1, 2. Having P1, not, there is no P1. Beam is assumed to be axially rigid. This is Q1, M1, Q2, M2. There will be 2 degrees of freedom at the nodes. These are the 2 nodes. It's a one-dimensional element having 2 nodes, 1 and 2. At each node, 2 degrees of freedom, shear moment. Beam is assumed to be axially rigid. If you have axial rigidity, then you can call it as P1. That is the frame. That is same as truss. PMI, whatever it is. Here it will be PM, P2. Right? If it is plane frame, same I am showing. That is orthogonal frame member, not inclined anchor. Okay? Beam, of course, it's okay. So having flexural rigidity, EI, length, L. Right? Now, you know from slope deflection equations, M1 equals 2EI by or 2EI by L into 2 theta 1, this M1 displacement rotation is theta 1, here displacement is Q1, or I'll say V1, this V2, theta. This is force M1 Q1, M2 Q2, displacements, corresponding displacement theta 1 V1, theta 2 V2. That I hope I made clear from the basic concepts. Likewise, if you have axial force P1 U1, P2 U2, you can call it. Instead of PMI, AJ, if it is confusing to notation, you can use single notation. Either way, it doesn't matter. So from slope deflection equation, you have M1 equals 2EA by L into 2 theta 1 plus theta 2, or again, before this, I will say sigma V equals 0. I will apply equations of equilibrium as I did in Truss. You will get Q1 plus Q2 equals 0, because they are the only two, Q1, Q2 are the only vertical forces, M1, M2 are the moments. Or you can say Q1 equals minus Q2, as you did in case of test P1 is equal to minus P2. Then if you apply sigma m1, moment about 0.1, 0, moment about 0.1, three equations of equilibrium. The one equation sigma h equals 0, I don't consider. Only other two equations, sigma is 0, sigma is 0. Sigma m1 0 will give you q2 into L is equal to plus m1 plus m2, q2 into L, q1 will not give any moment. Or q2 equals correct? This is what you have. So, out of q1, m1, q2, m2, four unknown forces, n forces, only two are independent. If you know m1, m2, q2 can be determined, then from this q1 can be determined. So q1, q2 can be evaluated by choosing m1, m2 as the unknown. So, same thing as I did in Truss element. Truss element out of two P1, P2, only one is independent. Here, out of four, two are independent. So, out of four unknown n forces, only two are independent. That is M1. So always choose only end moments as the unknown forces. Clear now? Why is it telling theory, basic concept I was telling. Which are the unknown forces to be selected? You can choose only two. You need not select all, only two you can choose. This is classical approach, some reduction. But in computer programming, choose everything, make one as zero or use the relationship. That's all. So M1, M2 as the unknown. So from slope deflection equations, M1 is given by 2EL by L to theta 1, theta 2, and that delta, there is no sway, because sway I am not considering, V1, V2, I am not considering, because I am not choosing it, Q1, Q2 are not independent. That's why I am not bothered about that sway. And fixed end moment, there is no member load I am considering, that also I will not consider, only this. And M2 is given by 2E by L, this will be 2 theta. That you know, slope deflection equation, relationship from basic structural analysis. Therefore, Q2 equals, or I will write this 2EL by L, theta 1, 4EL by L, theta 2 is 4EL by L, theta 1, 2EL by L, theta 2. Since Q2 is M1 plus M2 by L. Therefore, this plus this divided by L. Correct? So, that is 4EL by L, 2EL by L, 6EL by L into theta 1 plus 6 L into theta 2. 1 by L, M1 plus M2. This, it is that. Or this is 6A by L square theta 1 plus 6A by L square theta 2. And Q2 or Q1 equals minus Q2. Therefore, it is minus 6A by L square into theta 1 minus 6A by L square theta. Therefore, M1, M2 is equal to unknown forces is equal to 2A by L two, 1, 1, 2. This is nothing, or this is your Km member 4Pm, member unknown forces, member unknown and forces is equal to, this is Km, this is Bm. So that means for a B member with end moments only unknown, M1, M2, this is this displacement. But you can select M1, Q1 also unknown. M1, Q1 unknown if you select, then it is different. Because M1, Q1 if you select as unknown, then M1, Q1 as unknown, then you cannot determine. M1, Q2 you can select. M1, Q2 if you select as the unknown, M1, Q2 you can solve it, M2 can be determined, then from this Q2 also can be solved. So you can select either M1, Q2 or M2, Q1 also. So you can develop equation like this. So but usually we select only member and rotations. Displacement, vertical displacement invariably it will be 0. We have seen supports continuously. So that's why you remember for beam element with end moments is selected as the independent forces. This is the one. But here also if you use it, then it is a different thing. Okay? That time the remedy is just no, because time is over. It is good.